AEO.
We're going to break this video into two because there's a lot of examples at the end.
Sorry, but we want to do it justice.
It'll be homework for part 1, homework for part 2, because we don't want to be rushing through on the important practice.
Yeah, we really were.
This is really the first part of the packet that we have actual practice to do with.
We really need to be able to do it right.
Let's hit up the basics and the notes,
Take
and then
your
we'll
time.
get into the practice examples.
So factors that will affect how well I dissolve or won't dissolve.
There's really only 4 things.
Yeah, and there's really only 3, but first one is like dissolves like.
Right.
So how can I make something dissolve faster? Use a solvent that matches it.
Exactly.
Right, because like
if you know your molecule is polar, pick a polar solvent.
Correct.
And if it's not dissolving, pick a more polar solvent.
There you go.
Don't switch to non-polar because that certainly won't work.
Slow the process.
Right. It'll go in reverse.
Right.
The other thing is the phase of the solute. So if you're trying to get a metal to dissolve in water, good luck.
Right.
But it can happen. So you're going to have to play some games.
Yep.
Typically, solids and gases will dissolve in liquids. And solids don't dissolve into gases.
That's just a fact.
Liquids are either miscible, meaning will mix,
or immiscible.
Or immiscible, meaning won't mix.
Salad dressing.
Mm-hmm. They don't really dissolve. So oil and water, actually oil's on top, water's on bottom, they're immiscible.
Yeah.
But
shake it up.
Rubbing alcohol and water are miscible. When you go to the store and you buy a bottle of rubbing alcohol, it'll say
water.
70% alcohol, 90% alcohol. The other 10 or 30% is water. But when you look at the stuff, it looks all the same all throughout. So those are miscible. Oil and water, immiscible.
Right.
Now temperature. How does temperature affect solubility?
Well, temperature, this is the one we're really going to play a lot of games with. Solubility of solids will increase as the temperature increases. So those guys go up.
Curve up.
Okay, and the opposite is true for gases. The hotter I get now, the less is temperature. Here, why I wrote it opposite of what I'm saying. So we said we can absorb more gas as I decrease temperature, or I could say it the other way. I can dissolve less as I increase temperature. It doesn't work the same way as the solids do.
This relates to the kinetic molecular theory of gases, because the gas, as you heat it up, wants to be more ideal in its behavior, and that is not dissolved in the liquid. So as you heat this liquid up, the gases are like, oh, see ya.
Want to be a gas.
Their vapor pressure goes way up. They jump into the gas phase. They boil out very quickly.
Literally just have more kinetic energy. They're moving around faster at the surface, and off they go.
Now, pressure only works on gases. You can't put pressure on a liquid or a solid to increase its solubility. But if you want to change the solubility of a gas, you pressurize it.
Right. So your can of Coke, pressurized. You hear it. That pressure is to keep that carbon dioxide in the liquid.
Do not consume if seal is broken. That seal pressurizes the container. If it's no longer pressurized, that means the contents may have gotten in or out. It's not a sealed system. Your soda ain't going to be fizzy. Who knows what else got in there? And it's just not a good deal.
Yeah.
I'll pick up the pen for these. You wrote some good definitions. I liked your dynamic equilibrium.
Oh, dig it. Here we go. So we're going to do this again. We'll do it a little slower than we did it last time. You guys are going to take some notes on the picture, right? I have the solid in an unsaturated solution. And notice pieces of the solid are still going up into the liquid. So that's telling me that the liquid is unsaturated. That solution up top can hold more solute than it is because I see active dissolving. Okay. Now the second piece, the saturated solution B, this is our dynamic equilibrium. Because what's going on is there is dissolving happening. But now every piece that solid that dissolves into the solution, some piece of that solute in solution must drop out. So for every one that goes into solution, one's got to come out. And so that's what we call a saturated solution. It is holding as much as it can at that particular temperature. Solute-wise, cannot hold more. Okay. C is showing you that there's no solid on the bottom. Okay. And it says it's super saturated because it is really, really, really holding more than it can. That's that unstable piece, because with a little tap of that particular solution or a single seed crystal, and you get to see that cool picture that we did in the vocab about a supersaturated. Okay. Precipitate forms. This is when a solute or crashes out of the system. Okay, now we, in this class, for our case and purposes, is when I take two liquids and a reaction occurs and one of the products is now insoluble, it will form a solid and fall to the bottom, almost like it looks like it's snowing, like there's a snow globe. Started out two clear liquids, reaction happens, might take a minute, boom, it comes crashing out. That solid precipitate that falls out is a precipitate.
So I think this is the dividing line between the theory and the practice. So
Well, let's just check. Nope, we got a little bit.
A couple more notes,
Okay, so we'll call this
and
notes.
then we'll do all our
We'll
practice.
do all the practice. We'll
Mhm.
call this part of the notes, right?
Right.
So how do we use this table G with what's going on? So we got a minute, so I'm going to tell you. There's temperature on the bottom, and then there's specifically 100 grams of water on the y-axis. So by definition, saturation is when I fall on the curve, directly on the curve of interest. I am saturated. So let me give you an example. 40 grams of sodium chloride at 90 degrees. So Monaco's going to show you 90 degrees. He's going to find you 40 grams, and he's going to connect those 2 points. And then we're going to relate them to NaCl, our line of interest, and we just so happen to be smack dab on the line. On the line, saturated. Good?
Yep.
Any questions from you out there?
Nope.
Good, then we're moving on to the next one. If I fall below the curve, if I'm below the curve, I'm said to be unsaturated. I have less solute than I should be able to. 70 grams of KNO3 at 60 degrees. So we find 70 grams, 70 grams, 60 degrees. Match those two up. Now, compare those to our point of interest, which is KNO3. And notice I am well below that line. I could add that much more stuff into solution. That many more grams of KNO3 would still continue to dissolve if I continued adding. That's why I am unsaturated. Good? Good. Deep breath. Now above the curve. If I find out that I am above the curve, I am what's called supersaturated. I have more in there than I should be able to put in. So an example here, 110 grams of NaNO3 at 20 degrees. So notice he's picking the 20 degrees, he's picking the 110 grams. Let's plot that according to my line where NaNO3 is. I am way above it. So I have more in there than I should. That would be supersaturated. Now that is where we can, for the notes, and we will move on to next video, which will be some examples of how we manipulate this, because there's some games that we can actually play now, and we set ourselves up for those games. So,
So
see you next video.
4.5 incoming.
Yeah.
Where's my stop sharing button?